Hey everyone, and welcome. Our world is in constant motion. Everything from a planet zipping around the sun to the simple vibrations in a guitar string. But how do we actually capture all that dynamic reality in a way we can analyze and, maybe even predict? Okay, let's really dive into this.
So that's the big question, right? How can we possibly use the precision of numbers and symbols to describe stuff that's always evolving, or growing, or shrinking? Well, it turns out the answer lies in this incredibly beautiful and powerful mathematical tool.
And there it is. The language of change is written in what we call ordinary differential equations, or ODEs for short. And listen, these are not just some abstract formulas buried in a textbook. They are literally the sentences and paragraphs that tell the story of the universe in motion.
All right, so if it's a language, let's learn how to speak it. We're going to explore exactly how we translate what we see out there in the physical world into the mathematical grammar of ODEs.
This idea right here is the absolute core of what we're talking about. See, mathematical modeling isn't just about crunching numbers. It's a whole process. You set up the model based on what you see, you solve the math, and then, and this part is so crucial, you interpret that solution back into real-world terms. It's the bridge connecting what we observe to what we can truly understand.
So enough talk, let's build that bridge right now. We're going to take a super simple physical observation and see exactly how it becomes a mathematical equation, an ODE that we can actually work with.
It really is a three-step process, you'll see. First, you just observe something, like a radioactive substance decaying. Second, you state the rule in plain English: the rate it decays is directly proportional to how much you have at any given moment. And third, you translate that sentence into math. The rate of change, dy dt, equals negative k times the amount y. That little minus sign, that just tells us it's decaying, not growing. And boom, just like that, a real-world observation is now a clean mathematical equation.
And this shows just how flexible this language is. For simple unchecked growth, like bacteria in a petri dish, we use that exponential model. It's just like decay, but with a positive sign. But what about things that can't grow forever, like a fish population in a lake? For that, we use the logistic model. See that extra little term on the end, that minus by squared? That's the secret sauce. It acts like a brake, slowing the growth down as the population gets too crowded. Different physical rules, different equations. It's beautiful.
So, we've built our equations, but an ODE is a bit of a puzzle. It describes the rate of change, not the actual amount of stuff over time. To find that, we have to solve the puzzle. Let's see how that works.
Now, when we first solve an ODE, we don't just get one single answer. We get what's called a general solution. And it includes this thing called an arbitrary constant, that letter C, which means the solution represents a whole family of possible outcomes. It's kind of like having the right shape for the curve, but not knowing exactly where on the graph it's supposed to sit.
To find the one specific curve that matches our reality, we need a starting point, something called an initial condition. So if we know we started with, say, 100 grams of that substance at time 0, we can plug that information in and solve for C. This pins down the exact curve from that whole family of solutions and gives us the particular solution for our specific problem.
And how do we actually find these solutions? Well, mathematicians have built up a whole toolkit over the centuries. You've got some straightforward methods like separation of variables, but then you get into some really heavy-duty tools like Laplace transforms or power series, which are incredibly powerful for tackling the really complex equations.
Okay, this is where it all pays off. We've seen how to build them and how to solve them, so now let's look at where this mathematical language describes some truly fascinating and important systems out there in the real world. First up, pretty much anything that bounces, swings, or vibrates. Think about a simple mass just hanging on a spring. Its motion, how it oscillates up and down, that can be perfectly, and I mean perfectly, described by a second-order ODE. And here is its mathematical blueprint. This single equation, it captures everything about that system's motion. M is the mass. C is any friction or damping that's slowing it down. K is the stiffness of the spring. And that F of t on the end, that's any outside force pushing or pulling on it. It's all right there.
All right, now for something that seems totally different. The flow of current in an electrical circuit. Specifically, what's called an RLC circuit, one that has a resistor, an inductor, and a capacitor.
Now, take a good look at this equation. It describes the current, which we call I, in that circuit. You've got L for inductance, R for resistance, C for capacitance. Does that structure look kind of familiar?
It really should.
And this slide, this is the big reveal. The math is basically screaming at us that a mechanical system and an electrical circuit are, fundamentally, analogs of each other. The inductance in the circuit behaves just like the mass. The resistance acts just like the damping. The spring's stiffness is like the inverse of the capacitance. So here's the mind-blowing part. By solving the equation for one system, you've secretly solved it for the other. This is the true power of mathematical modeling.
So, let's bring it all together. We've gone all the way from just watching the world to writing its rules in the language of math. But what's the ultimate goal of all this? Where are we going?
It all comes down to prediction. Simple as that. Once we have a model that accurately describes a system, we can start asking, what if? What happens if we double the mass on the spring? Or what if we lower the resistance in the circuit? The ODE gives us the answer, letting us predict the system's behavior without ever having to actually build it.
And that really just captures the spirit of it all, doesn't it? ODEs are not just a topic in a math class. They are a fundamental tool, a compass, that allows us to navigate and make sense of this complex, dynamic universe we all live in. They are the language of how things change.